to do your math homework. So I'm going to collect it the last week, only knowing the psychology of the student, having been one myself. That's for all homework? No, I mean, the last homework assignment is due. Oh, no, there's no, I don't take anything during final. No, no, there's no like last minute desperation scramble to get homework in. And then 8 days after the final, I get like, oh, please, can you take my 9 assignments? No one would do that. Nobody in here would give me 9 assignments.
Yeah, we weren't even assigned 9.
Yeah, right. No, so yeah, so let's make that clear up front, right? I'm not going to take any homework after Friday of dead week, right? So during finals week, that's like it closes, homework closes, and so corrections and stuff like that can come in during finals week, but not after the last day. I will take that as the day of the final. Okay, finals over, the class is done. Yep. Midterm 2 corrections. I don't. So the only reason that so the point of having the midterm 1 corrections was that a lot of people kind of got blown up on exam 1 because it was the first time that a lot of people taken a serious proof-based exam. There won't be enough time, and you're going to have to trust. You're going to have to trust that when I calculate the scores at the end, the scores people get in this class are going to be relative to the general performance of the class. So if everyone gets crushed on exam 2, which it doesn't look like is what's happening, but you know that should be accounted for in the final grades. Now, if it turns out that there's something I want you guys to revise because I think it's important for the final, I will offer that as well. Okay. So that's also part of my. I've graded problems 1 through 3 and half of problem 4. So those are also going to be finished tonight. So you'll have be back tomorrow. Yep.
So for revisions on the final homework, like will we do revisions on the final homework?
Probably not. I mean, the whole point of the revisions on the homework is to give you guys the opportunity to rework stuff, right? The points themselves don't count for much. I mean, it probably feels to you like the incentive is the point, but from my point of having you guys do that is to go back and do stuff you did incorrectly and look at it again, right? So it's not really costing you much to, I mean, the last homework isn't going to be able to be graded probably even in time to get it back to you, right? If you do want it graded, you can get it to me early, right? And so I'll be able to give it back, but that's going to be your responsibility with the last homework is if you guys have stuff that you really want to see, and I'll give opportunities for this in class, you have to ask me the homework questions so we can go through them or come into my office hours so we can do them. And don't trust the answers you're finding on linearalgebras.com either, because that guy sometimes leaves huge holes in the arguments that he makes. So I know nobody's going there, except when I see his terrible arguments in your homework exercises. But I'm not going to name any names. I myself have referred to linearalgebras.com on occasion. So the plan is the following. So we have 5C, which we started talking about last time. I'm just going to point out, I'm going to talk about the big sort of diagonalization theorem, and then the one time in this class that we know we can find a diagonalization for an operator. So we're going to finish 5C. And then we're going to talk about 6.1 and 6.1. That's not how Actor does things. 6A, 6B, and 6C. 6A and 6B are about inner product spaces. So this is the dot product exists on Euclidean space. Right? A dot product is a thing that makes sense. So how do we come up with a notion of a dot product for an abstract vector space? And that's important because I want to be able to say that things are orthogonal to each other for an abstract vector. So we'll talk about inner product spaces, and then we're going to use them to talk about something called the fancy phrase for it is orthogonal optimization. And you guys have seen this in the past as least squares. So the big question that we're going to answer in the last part of the class is basically this. Suppose the point of all of this. The point of all of this is it's possible that I might be able to write down a problem in a vector space that's not solvable, right? You can imagine that if you have T in L, let's say it's in LV. So I've got some operator, T in LV. It might be possible that W, which is an element of V, is not in the range of T, right? That's pretty easy to imagine happening. It's possible the range isn't all, not every operator is surjective. But I might ask the question, solve this problem anyway. So even though W is not in the range of T, I might say, solve this problem anyway. Find a V in V so that TV is equal to W. Now, is that problem possible to solve? If W is not in the range of V, can I solve the problem, find a V that T turns into W? No, V is not in the W. I'm thinking of this is unknown and this is unknown and this is the unknown here, right? Find a V that makes this equation hold. And the answer is this is impossible. Impossible, you say. W is not in the range of T. To which the response of the linear algebraist is find it anyway. Do it anyway. Okay, find V anyway. And the picture of what we're doing here, when I say find V anyway, what I mean is if you imagine that you have the range of the operator T, which is a subspace, right? Range of T is a subspace. What I'd like to do is be able to say, well, the range of T is every single thing that could possibly come out of T. And suppose V is a vector that pokes out of it like this, or sorry, W. W is not in the range of T means W sticks out of that subspace, right? It's not in there. I can't find a V that does this because W is not in the range of T. So we're going to build a theory that's going to let us draw this picture. I might not be able to find a vector V, since W is not in the range of T, I might not be able to find a V that does this, but maybe I could figure out the closest vector down here. This vector is the closest vector to W that's in the range of T. But of course, to do that would require having a notion of projection of vectors, right? Essentially, what we want to do is project the vector W onto the range of T and solve that problem, which is solvable. So we're not going to solve this problem. We're going to solve the nearest possible problem to solve. And this is called least squares approximation. You've seen it if you took statistics and you did linear regression. That's this problem. So this is called orthogonal projection. So everything we're doing with inner product spaces is to come up with the idea that this projection exists. This picture makes sense. So we're going to solve an impossible problem by changing the problem and getting an answer that's good enough. So if you know the punchline here and you know how to do this, don't say anything. It's pretty easy to do with matrices. Actually, I'm going to poll you guys real quick. How many of you saw least squares in 206? Not many. Okay. So or this sort of like orthogonal. Do you see orthogonal projections on the subspaces? That's going to be close to the end of the class probably. You see projection on the subspaces. So we're doing that idea, but we're going to do it in abstract. Okay. So that's kind of the goal of the rest of the class, is to make that story coherent, like to make that a meaningful operation. So yes.
When you say abstractly, like an abstract vector space,
yes.
What do you mean by that?
So basically, what everybody has seen before in previous classes, what most people have seen, if you've seen this in the context of V being equal to Rn, and where there are no operators. You didn't learn operators, you learned matrices, right? So you learned V is Rn, and every T of X, every operator T in L of V, in a 206 class, T is not a general operator. T is always thought of as being a matrix A times X, where A is a matrix. So when you learned eigenvalues and eigenvectors, you learned the matrix version. When you learned projection, you learned the matrix version. You learned it with the original dot product in Rn. So we want to take the idea of a dot product in Rn and projections in Rn and working with matrices in Rn, and instead work the way we have been, where we're talking about operators in a vector space instead. So I don't mean anything more than we've already been doing, right? We use Rn as an example, but we hardly ever build these theorems so that they're only true about Rn. Okay.
Can I ask you? It's about the definition of locus.
Yes, that's what the first thing we're gonna do is talk about it today. All right, so hit me with it. What is it?
Is the diagonalizable definitions. So an operator is diagonalizable means the matrix of that operator can be diagonal.
No, it means a little bit more than that. I mean, so T is diagonalizable. It's an existence definition, right? T is diagonalizable if there exists a basis V1 to Vn so that M of T with respect to that basis is a diagonal matrix. I wrote it in the backwards order yesterday because I was writing it like Axer did, but this is the definition. You can find a basis for the vector space so that the matrix turns out to be diagonal. It won't be the case that every basis gives you a diagonal.
Yeah,
matrix.
that was the
No,
next question.
no, it's a special thing to be able to do this.
Okay.
Yep.
So,
Were there more?
no, I just don't understand why. Like, why not all bases?
Well, this is actually pretty easy to show with an example. So even in the sort of Rn case, if you imagine, say that you have an operator Tx, which is equal to 1, 0, 0, 1 x. That's not a very complicated. That's not a very complicated operator, right? It's the identity operator. Actually, that's not what I'm going to do. Forget that. Let's do T of, am I going to be able to do this quickly? T of UV is equal to U plus V. Hold on, I'm going to have to build you a question in order to make this make sense. So, T of U and V is equal to 2U plus V, U plus V. Okay. Now, if you write this down and you write down the matrix for this, so if you suppose this is your operator and you're going to let, this is an operator T that's an element of linear maps on F2. Okay. So if you choose a basis, for F2 that is 1, 0, and 0, 1. So suppose you let V1 be equal to 1, 0 and V2 be equal to 0, 1. That is a basis for F2, right? This is a basis for F2. Okay. If you write down the matrix of T with respect to that basis, you get this. That's what it does, right? T takes U and sends it to 2U plus V. And T takes V and sends it to U plus 2V. That's where the 1 and the 2 come from. So this is the matrix of that operator with respect to that basis, right? This is how you compute the matrix of an operator. You compute the matrix of an operator by looking at it what it does to the basis elements. This is the matrix. I leave it as an exercise to the reader to prove that this is the matrix for this. This is the matrix for T with respect to this basis. Okay, is that diagonal? Is that diagonal? What is a diagonal matrix? There should be no hesitation. There should be no hesitation about this. What is a diagonal matrix? Something 0, 0, something. 2 by 2 diagonal matrix has things on the diagonal and nothing else. Only on the diagonal can non-zero entries be. Is that diagonal? No, this is not diagonal. And yet, I claim that this operator is diagonalizable. I can find a basis that makes that into a diagonal matrix.
But not this basis.
Not this, well, no, in this basis, it's not diagonal, right? With this basis, I did not get a diagonal matrix. But with a different basis, if I'm careful about the way that I choose it, if I'm careful about the way I choose a basis, the matrix will be diagonal. And the secret is going to turn out to be that if I had used eigenvectors here instead of the 1, 0, and 0, 1, the matrix would have been diagonal. Sure.
Yesterday when we were just writing out the definitions,
Yep.
like the diagonal matrix
diagonal, like, the definition says only like non-zero. and
If
one
if
diagonal.
any non-zero entries can only appear on the diagonal, you can still have zeros on the diagonal, but you can't have anywhere anything else that's not zero, right? So there can be zeros on the diagonal. You could have zeros on the diagonal, but you can't have anything but zeros off of it. Right. It's mostly zeros, right? It's mostly zeros, and if an entry is is of the form is a non-zero entry, it must be AII for some I. Right. So generally, when we think of a diagonal matrix, we think lambda one. In fact, oftentimes you'll even see this written where no other symbols are even written because the only non-zero entries in the matrix are the ones that are on the diagonal. So yeah, I kind of changed definitions, I guess, a little bit, but not bad. Yep.
Is there any significance between row reduction?
Ah, now that is a good question. So we haven't talked about row reduction or the row reduction algorithm yet. And it's not really part of the class here, right? But the idea is that if the invertible matrix theorem says that like something about row reduction. So the answer is no. What you would hope to be true is if row reduction worked, what you could say is that you could row reduce it to a diagonal matrix. What you can row reduce to is you can row reduce to an invertible matrix, an identity. If you can the theorem you're thinking of is, okay, if I row reduce to the identity, it's invertible. That's not good enough for diagonalizability. Row reduction is not the tool we want because we have to use eigenvalues and eigenvectors instead. This is why this is a hard problem. Invertibility is a much easier question to deal with. Okay, so you look at this matrix and you think to yourself, okay, what are the eigenvalues and eigenvectors of this problem? And then you give up and you go over here to Wolfram Alpha and you punch that matrix in real quick because I don't want to do matrix algebra in front of the classroom. Unless one of you guys is good enough to know off the top of your head what the eigenvalues and eigenvectors are. No? All right. So this operator T has the eigenspace associated with 3 of T equal to the span of 1, 1. And the eigenspace associated to 1 of T equal to the span of minus 1, 1. So if you did the algebra and you did the computation, this is what you would, there's a computation where you would find the eigenvalues and eigenvectors. You have to solve, it's complicated to do that because you're going to get a system of equations you have to untangle. But if you did, this is what you would get. How did I do it? I put it into Wolfram Alpha and told it to row reduce the matrix for it. Or not row reduce it, to find the eigenvalues and eigenvectors. Okay, so now what does that say? That says if you chose V1 equal to 1, 1 and V2 equal to minus 1, 1, then the matrix of T would be equal to 3, 0, 0, 1. In this basis, the matrix of T is diagonal. In this basis, the matrix of T, same operator, right? The function is the same function, but the representation of the function changes based on the basis that we pick for the space. This is like why eigenvectors are so useful. If you have enough eigenvectors, you can do this where the eigenvectors themselves tell you what the diagonal matrix has to be. So I invite you, walk through this example and see if you can show that this matrix is what I say that it is. You don't have to find these if you don't want, because it's annoying. But starting from this point, you should believe that if you start with this, this is the matrix for T. And I'm telling you, this is the same function. Same computation, same function. Okay? This is really nice, but it requires that I know these to get it. And of course, the point I made last time was it's sometimes not possible. So if instead I had started with, I think I pointed out last time, if instead you start with an operator S of UV that was equal to U plus VV, that's not diagonalizable. And the reason this isn't diagonalizable is because it only has one eigenvalue. And it only has one eigenvector. So one eigenvector is not enough to be a basis, so you can't diagonalize. And this is a hard question to know when this happens and when this happens. In fact, the first theorem I want to write down today,
Why are like similar matrices with diagonal?
What do you mean?
Isn't like when matrices are similar, don't they have to be diagonalizable?
Okay, so no, a matrix is called similar. So I'm gonna take the time to do this because this kind of links together like the linear algebra of the past and the linear algebra of the present. Okay. So when you say two matrices are similar, what you're saying is that there's an invertible matrix that lets you get from one to the other. So A is similar to B means A is equal to SB S inverse for some invertible S, some matrix S. Similarity basically means that that A and B are the same up to a change of basis of a vector space. Right? We haven't talked about change of basis, but in matrix language, that's what it means. Now, another way of talking about diagonalizability in 206 is an operator as a matrix, a linear map is diagonalizable if it is similar to a diagonal matrix. Okay, that's where that word would have been in the 206 class. Right? We're not using that because we're not really doing matrix theory in this class. But that's where you would have seen that before. These ideas are all linked because you can always work with matrices. Okay, so when do I actually know for sure that I have a diagonalizable matrix? So this is sort of the keynote theorem of this chapter. Says the following. You guys can, this is another one where you can give me a one-line proof. In fact, did I do this one last time? Did we do the one-line proof argument? Suppose that V is finite dimensional. Suppose V is finite dimensional, and the dimension of V is equal to n. And suppose T is in L of V, so T is an operator. And suppose lambda 1 up to lambda n are distinct eigenvalues of T. Then T is diagonalizable. What was it? The most important theorem about eigenvalues and eigenvectors. The distinct eigenvalues have linearly independent eigenvectors associated with them. So this theorem is true because if you have enough eigenvalues that are different from each other, then the eigenvectors must be linearly independent. Each eigenvalue, here, this is what a proof of this looks like. Is an actual proof of sorts. To be a little bit less formal than Axer's proof, right? Each lambda I has an associated eigenvector vi, of course, not equal to 0. And here's a claim. A1 v1 up to an vn is equal to 0 has only a1 equal to a2 up to an equal to 0 as a solution. Why is that true? Because they're linearly independent. Each one of these is associated with a different eigenvector, right? Because eigenvectors of different eigenvalues are linearly independent. Okay, how do I finish the argument? That means I have n linearly independent vectors. What's the dimension of V? N. So what can I conclude? The basis. So V1 through Vn is a basis. Because linear independence and spanning are equivalent to each other in an n-dimensional space if you have n of them, right? Well, if V1 through Vn is a basis, there's that big theorem we proved last time with the 5 equivalent, or that proved the theorem we laid out, you guys were supposed to read the proof of, with the 5 equivalent conditions says that if you have a basis of eigenvectors, then the operator is diagonalizable. Then P is diagonalizable. Because B has a basis of eigenvectors. This is a typical kind of argument that it uses that. Yep.
Here, let's see, or your basis of C vectors.
Yeah.
Show. I understand the significance of showing that U1 direct sum to UN equal to V, and that it's invariant with G. Direct sum part is not obvious, but
So hold on. It's B implies C that you're asking about. I'm rolling back to that chapter here. Okay, so the big theorem, we've got B implies C. So he says, and suppose B holds, and B is a basis. There exist one-dimensional subspaces, each in invariant over T. Well, but isn't that the whole point? Is that, what do you mean? The conclusion of part C is that you have
well, yeah.
a direct sum of invariant subspaces. So what is it that you don't understand the?
Why you bring that up? Why is it a big deal if they're invariant?
Okay, so the idea is that like you're trying to have as many different, I mean, the whole point, the whole point of thinking about invariant especially one-dimensional invariant subspaces. Every one-dimensional invariant subspace is multiplication by a scalar, right? I mean, it has to be. It's multiplication by a scalar. So that it forces an eigenvalue to exist. I mean, it's a way of thinking about eigenspaces as fundamentally just invariant one-dimensional subspaces. So, and you do it because like when you're working with vector spaces, a lot of times you want to work with geometry. This is a geometric argument. So you're saying you've got this algebraic condition that corresponds to something like, oh, well, what does it mean to be an eigenvalue or eigenvector? Well, you've got like sort of like a beam counting argument that says you have enough eigenvectors that are linearly dependent. And then you have a geometric argument that said the space decomposes into a bunch of invariant subspaces. Sometimes you want to think about the subspaces as the important object, and sometimes you want to think about the beam count as the important object. So it's not necessarily independently anything other than a different language to use to think about it.
Direct sum will hold even if they were eigenvectors.
What do you mean?
If you want to be under the basis and split each one into one subspace, the direct sum of all those subspaces will be.
Yeah. It's the invariance that fails there, right? It's the direct sum is as a consequence of the basis, right? It's the fact that you have the invariance that gives you the direct sum structure. Or sorry, the invariance matters because the invariance, it's going to eventually end up carrying an idea of orthogonality. We can't talk about orthogonality yet, but it's headed that direction. So it's basically an orthogonal decomposition of a vector space. We can't talk about that because I haven't explained to you what orthogonality is. So yeah, he's setting the stage for a future result. Okay, so are there questions about anything to do with diagonalization? That's it. We can't say anything else right now. Nothing. I can tell you nothing else about when things are diagonalizable and when they aren't, because we have no tools. It takes 3 more chapters of this book to build the tools needed to say when anything else is possibly diagonalizable. So if you want to see the rest of the story, you got to go through 406. Yep.
Why is diagonalization important?
Diagonalization is important because if you're ever working in any sort of computational or pure setting with matrices, you want to work with the maximal number of zeros possible. In fact, many theorems are obviously true with diagonal matrices that are very difficult to see otherwise. So if I have some enormous matrix and it's full of zeros and I multiply it with some other matrix, like it's really easy computationally to do that. So a lot of approaches to problems involve first diagonalizing the matrix, then doing insane computations with it, right? So if you have to take really high order powers of a matrix, you'd really like to spend the time to get a diagonal first and then start working with it, right? And then undiagonalize at the end. So it's a computational trick, it's a theoretical trick. It's in math, in applied math, you want to work with the simplest version of an object, and it's a structurally very simple, and computation very simple.
So like an upper triangular matrix is better than just
Yes.
diagonal.
Even better than that, yeah. Yeah. And in fact, another part of the story in 406 is what do you do if a matrix isn't, what do you do with an operator with not diagonalizable? And you have to learn this entire theory called Jordan form, right? Which is, there were some particularly unenthusiastic responses to that from the people who are currently in 406. And I will tell you that when I took Nat 406, I refused to learn Jordan form because I thought it was irritating. So I just, in a moment of like sort of mule-like stubbornness, I said, I am not going to learn that. I don't care if I fail that question on the final. And then I did fail that question on the final because I refused to learn it. But I stuck to my guns and I never learned Jordan form until I had to teach it. And then I thought, man, I was an idiot. Why did I do that to myself? Okay, so let's leave sort of esoteria for a second and let's remind ourselves. About one of the most useful and pleasant objects that exists in Rn. So here's an old friend. For x and y in Rn, the dot product of x and y is x dot y is equal to the sum of xi, yi.
Sorry, this one bothers me. Could you change it to 6 today?
Oh, sorry. Axler, 6 dot Axler. And then this is a sum that runs from -1 to n. To remind you what I mean here, I mean, if you had something like x1, x2 dotted with y1, y2, that would be equal to x1, y1 plus x2, y2. Good old scalar product Rn. So this has some pretty useful properties that we want to lift up to abstract setting. I mean, because you have to be, there's properties that, because when you learn this the first time, you don't know about the complex, you're not allowed to know the complex numbers exist. So when you learn it the first time, you learn it this way. And even just this version of it carries properties that we want to lift up. And we are gonna do it on an F once we generalize it. This is like the 206 dot product. So this thing we're going to lift up to sort of abstract setting in the 306 version right now. So we're going to identify some properties that it has, and then we're going to try to make a definition that replicates as many of those properties as possible. Okay, so some properties that you might notice is that with this definition, x dot x, which is a number, is always positive. It has to be, because x dot x is just the sum of the squares of the entries of a vector. X dot x is the sum of xi squared. Of course, that's got to be non-negative, right? Sum of squares, non-negative. And what? Oh, there's another thing, which is, man, that looks an awful lot like the length of a vector, except maybe squared, because the length of a vector in Rn is the square root of x1 squared plus x2 squared out to xn squared. We just define that to be the length of a vector. So this, the distance formula, right? Well, if you square both sides, you get this. And that's weird because that looks an awful lot like x dotted with itself. So it turns out that the length of a vector, so I'm just reminding you, so everyone remembers this. The length of a vector squared is equal to the dot of the vector with itself as well, right? So the dot product and the length of a vector are associated with each other, right? They're related. Okay, if x dot x is equal to 0, then x is 0. The only way to dot a vector with itself and get 0 out, the only way to have a vector that has length 0 is to put the 0 vector in. So think about this as property 1, and property 2, property 3. And finally, we get this kind of nice property here. It's not finally, actually point out 2 more. X dot y is equal to y dot x. That one's going to turn out not to be true in F, but we'll write it for now. Symmetric, or commutative rather. And then finally, he points out that you can define a function f of y is equal to the dot product of x with y is a linear function. So if I fix some vector x and I define a function that says eat a vector and take a dot product against another vector, that's a linear. So what on earth are we going to do if I don't have coordinates? Because I don't. In an abstract vector space, I don't have any coordinates, right? There's no numbers running around inside of a vector. All of this is assuming that x is equal to some list of coordinates in R. So what we do is we say, well, throw away the function and keep the properties. And anything that satisfies the properties of a dot product, we're going to call a dot product. So we're going to use this as a way to generalize this idea. So here's the definition. So the definition of an inner product is supposed to generalize the idea of a dot product. So all these properties that we wrote over here, we want to write down over here in the general setting. Okay, so an inner product on V is a function that takes an ordered pair UV, where U and V are vectors in V, to a number. He's going to use lambda here. No, he doesn't. He's going to use the symbol UV contained in the field. Okay, so this is supposed to be the output. This is a number. So this represents the output of applying the function. So when he uses angle brackets, he means whatever you define for your dot product, it's a number that comes out, satisfying the following properties. Let's see. 1, positivity. Which is to say BV is greater than or equal to 0 for all B. This is going to seem abstract, but we're going to make it concrete in a second. Some examples. Yep. I'm taking the dot of, I'm thinking of this as the same thing as taking a dot product, but so you can imagine this is acting like a dot product, right? I'm saying, I haven't told you anything about what an inner product is, except it's a function that's going to act like a dot product. When you take a dot product of two vectors that are the same, you get a non-negative number. I'm going to make it part of the definition of something to be an inner product, that if I take the inner product of two vectors that are the same, that it's non-negative. This is a definition. There's no theorem here. I'm just defining the thing that is what's called an inner product, okay? It is exactly what it is.
And then
Go
by
ahead.
generalizing.
I mean that the V itself doesn't have to be Rn anymore. V is just a generic, like an abstract vector space now. There's no Rn. There's no coordinates. There's no vectors. I can't write the sum of the entries of V squared. Okay. There's no coordinates anymore. Just vectors. Let me get through the definition. I'll give you guys some examples of some things that are not the dot product that still do all the same stuff as a dot product. Okay. 2. Definiteness. V dot B equals 0 implies that V is 0. That's not even, we'll just go all the way to if and only if. 3. Additivity. In the first slot. Okay, what do I mean by that? I mean, U plus VW is equal to UW plus VW. I can split dot products. I mean, the dot product does this. It can split into pieces like this. We want this to be a linear. Remember, this is supposed to be keeping track of the fact this is a linear function. So we've got positivity, dot products producing 0 if and only if the thing that went in was a 0 vector, that it's linear in the first spot. we'll finish up linearity because we also need homogeneity in the first slot. I already know, like, the question, like, well, what happens in the second slot? Why are you just doing it in slot one? So homogeneity in slot one says lambda UV is equal to lambda UV for all U and V and V, and for all lambda field. So these two conditions together make the dot product linear. Additivity and homogeneity is the definition of a linear function. And the final thing that we want to do here is I didn't tell you anything about what happens in the second slot of this object, of this operator, and this is where we have to deal with the fact that complex numbers exist. We want symmetry, right? Commutativity, but we have to be careful because with complex numbers, to make everything work, we need this to be true. UV is equal to VU, but with a complex conjugate put on top. So this is called conjugate symmetry. So that is not a feature of the dot product in Rn, but it comes with the dot product in C. You were asking about why not in the field. This fixes the field thing. Yep. Definiteness. So positive, definite.
These are number, not vector.
All the things that you should think, when I'm writing down here, every one of these symbols is a number. Every one of them. It's a number in a field. So what the inner product does, I'm going to use like the old like machine analogy here. So you can think about what the inner product does is it has two spots to put things. And you feed it a U and a V, two different vectors, and what comes out is an element of the field. So it's a way of turning two vectors into a number. This is exactly what the dot product does, by the way. The dot product takes in an X and a Y in Rn, and then it grinds them up and it spits out X dot Y, which is an element of R.
Oh, so you're right. That notation's that's kind of like X dot Y, right?
Yes.
Okay.
Every time you see this by analogy, you could think U dot V. It's not U dot V in the Euclidean sense, but you can imagine that it is if you're trying to keep track of what's going on.
It looks like a vector.
Yeah, okay, yeah. So there's going to be a big difference from those of you guys that have worked in earlier classes with vector or different classes where to distinguish between a point and a vector, like a lot of authors use these angle braces to tell you this is a vector as opposed to it being a point. Here, when I use angle braces and when Axler does, I mean the thing that acts like a dot product. This is a function now. Notice Axler nowhere has made a distinction between points and vectors in this entire class, right? So when you see that angle bracket, you can imagine that it's like a dot product. Some authors don't even use the angle bracket notation. They just use the dot. Yep.
We need two vectors and a 22 value after the dot product, which is the value.
Ah, now that's a good question. In fact, why would I be defining any of this unless it like that question had some meaning? So I'm going to give you the motivation for this. The original motivation for setting up this definition is the following. Suppose I gave you the vector 1, 0 and the vector 0, 1, and you drew them in the plane. What would you notice about them? 1, 0, and 0, 1. You notice anything about those vectors? They're at a right angle, right? They're right. There's a right angle right here, right? The angle between these vectors is 90 degrees. What is the dot product of 1, 0 and 0, 1? 0. So, in fact, generally in Rn, what we do is we say, oh, well, notice that X is perpendicular to Y always means that X dot Y is equal to 0. We use this idea all the time when we're doing Euclidean geometry, right? What we're going to do with the one thing that we're going to say, meaning that we attach to the value that comes out of this, is we're going to define it to be the case that if the value that comes out is equal to 0, then we're going to call those vectors perpendicular. So the first thing we're going to do is we're going to come up with an idea of angle in a generic vector, in a sort of a general vector space. Once I have this, I have a way of telling when things are perpendicular to each other or not.
So do we only care when the dot product equals 0?
You can get way more out of it than that. The dot product is going to be the central tool that we use when we build our theory of projections. The this inner product is going to tell us something about vector projection. So if you remember the vector projection formula from 206, it involves dot products of vectors, right? The vector projection formula in matrix land looks like, oh, I take the projection of a vector B onto A. That's a picture that looks like this. Here's B, and here's A. And you draw this vector right here, and you can define the vector projection of B onto A is equal to A dot B over A dot A times A. That's the thing you do in Euclidean, in sort of Euclidean vector spaces. You do that projection formula, but it has dot products inside of it. If I want to remember, the point at the beginning was I'm trying to come up with a way of solving problems that can't be solved using that projection picture. How am I going to define a projection in an abstract vector space? I need something to replace these dot products to do vector projection. And the thing that's going to replace the dot products is going to be one of these guys. Then you can't project. I mean, it's not that it's not zero. It tells you that the vectors point in the same direction. That's hard to draw. If two vectors aren't, if the dot product of two vectors aren't zero, it means they're not perpendicular to each other. It means that there is a projection of one onto the other one. We'll talk more about this next time. I ran out of time before I gave you guys an example here, but we'll talk next time about examples of things that act like this that are not the Euclidean dot product. And then we're going to use this sort of ideas to prove some properties of inner products. And ultimately, the idea is we want to come up with a formula that lets us do vector projection, but in an abstract vector space instead of regular Rn. Because ultimately, we want to solve the unsolvable problem. W is not in the range of T. I want to find the vector that solves the question anyway, right? I want to find this vector, which is going to require that this is a meaningful thing, that this projection works. And that's what this is for. Right? What?
I'm back.
Yeah, all right.
How do you feel?
I think I did pretty good. You didn't grade it yet, did you?
I thought I did a lot better than
Yeah,
that.
I'm eager to find out. Wait, which midterm? 242. I'm eager for this one too. 242. This one, let's do tomorrow.
Oh, really?
Yeah.